Hi, my name is Dave Lannom with Monroe Training, and welcome to today's segment on basic electricity. Let's go over our agenda real quick. What we're going to try to do today is make electricity absolutely simple. We'll talk about the three pieces of electricity. We're going to talk a little bit about potential voltage and also introduce the concept of voltage drop. Then do a demonstration, and then we'll do a quick summary. But above all else, we've got to keep it simple. I mean, put it this way. I mean, let's say I gave you a battery, a couple jumper wires, a socket, and a bulb, and I said, okay, here's what I want you to do. I want you to light the light bulb. I don't think anybody that's listening today would say that's a problem. So, what if we made it really complicated and we throw a switch in there? Again, still not that big of a problem. And then, well, we couldn't do this unless we were safe. So, we'd have to put a protection device like a fuse in. Again, nothing that is that complicated. And if we will always keep electrical circuits in our mind that simple, it'll make it work for you each and every time. So, what about some of you that have been to advanced schools and you're like, okay, what about that Ohm's law thing? Man, we spent weeks calculating volts and amps and ohms where we knew that volt was always equal to the ohms times the amps, and ohms was volt divided by amps, and amps divided by was always volts divided by ohms. I mean, at the end of the day, I've never solved a automotive repair problem with math. So let's keep it simple. When we start to look at Ohm's law, I simply compare it to water. I mean, think about it. Voltage is really a pressure that can be pushed into circuits that we measured in volts. In other words, it's basic water pressure. And we talk about amperage, it's the flow of electrons. It's, the more we restricted the flow of the water, the less water came out. So if we had a big spigot, a lot of amps came out. If we had a little spigot, just a fewer amount of amps came out. Just like water, electricity is the same way. It's kind of interesting. When we talked about opposition to current flow or restriction, resistance, and that's measured in ohms. In other words, if I have no resistance, I have flow. But as I increase the amount of resistance, at that particular point, it's harder for anything to flow. I kind of like the cartoon version. It makes it a little bit easier for me to remember. Volts, the pressure that's pushing the amp. But not as many amps can get through if those ohms, the resistance that's measured in ohms, starts to restrict the flow. And as soon as that resistance measured in ohms restricts the flow, we can't push as many amps through it. It really is that simple. Because when you think about electricity, there's really only three pieces. We've got a source, which, except for starting, that's pretty much the alternator. I mean, we use the battery to start the car and serve as a buffer between the electrical system. But while the vehicle's running, if everything's going well, the alternator is what's really powering the car. So if we had a source, all we need is a load. And the load, very simple definition, is it's the component that does the work. That's the fans, the lights, the heater grids, anything that's performing work in the car, that's the load. And a load is always going to have resistance. And remember that resistance is measured in ohms. What's the last thing I needed? I need a complete path for the current to flow. But that's not just the wires. Don't forget the chassis ground. I mean, it's just very economical if we literally energize the vehicle's metal chassis. We attach a ground from the battery to the metal chassis at that particular point. Anywhere that we are in the vehicle, instead of running a wire all the way back to the negative post of the battery, we can simply attach that to a body ground. And I'm talking about that because as we go through some diagnostic processes, and the more we learn about electricity, the more those grounds are going to get in our way. So don't forget the ground. So let's talk just real briefly. We're going to do a whole segment on all the schematic symbols, but just for today, I want to make sure that we've got this really kind of simplified before we do anything. So if we look at the images, we see a battery is represented by what kind of looks like a bunch of bars. And when I'm looking at a schematic, that longer bar is always the positive plus. Then we take take a look at the fuse. And the fuse symbol looks kind of like an S. The lamp even looks like a lamp, and the switch is obviously the switch. Now, what we did here is you notice that there's a little checkerboard pattern behind both the battery, as well as the switch. And the reason that's there is those are the two areas in a circuit that I'm going to see potential voltage. So let's talk a little bit about potential voltage. If I take my meter and I hook my meter up and I measure across a battery, I've got 12 volts. Okay, there's some people out there that say, wait a minute, Lannom here, a fully charged battery's got 12.7 volts. Okay, I'm good with that. I understand that. But for what we're doing today, just talking about electricity, let's keep it simple with right about 12 volts. So if I measure the volt potential across that battery, it's 12 volts. But let's say this. Let's say I just hooked up a set of jumper cables in my battery, and then I measured the voltage at the jumper cables. What do you think I get? Yeah, you're right, 12 volts. Again, there's no electricity flowing. There's simple potential voltage. So let's talk about the difference between the potential voltage that I have and the voltage that we use. So we build that simple circuit. We take 12 volts and we feed it to a light bulb. At that particular point, if I measured the voltage at the battery and I measured the voltage at the light bulb, both of those should be the same, 12 volts. Real fancy technical guy came up with that, some guy named Kirchhoff, and Kirchhoff said this: if I put 12 volts into a circuit, all 12 volts gets used. Now, I mention that now because when we start to talk about voltage drop, we start to see problems in circuits. That's when Kirchhoff's law, you can say, hey, hang on a minute here. There's got to be 12 volts in, all 12 volts has to be used. And if I can't see it where it should be, I've got to measure where it should. So at that particular point, let's say we break the circuit. We just cut the wires. Now, what changed? Let's say I measured across that open circuit. Now, even though there's no electricity flowing, there's a complete path to ground through the light bulb, as well as a path to ground back to the battery, or battery positive, pardon me, as well as battery positive potential back to the battery. So if I measured the voltage across an open, there's no voltage being used because that circuit's open, but I'm still going to measure that 12 volt potential voltage. So let's say we did the same thing. Let's say we intentionally opened and closed the circuit. Now, at that particular point, with that switch open, the light bulb's off, but I'd still have potential available for 12 volts. But what happens when I close that switch? When I close that switch, where should the voltage be? I mean, the voltage at that point, I should have 12 volts at the battery and 12 volts at the bulb. So when I hook my meter across a closed switch, I should say little to zero voltage because the voltage should always be at the source and again, the load. The same thing's true here. We put a fuse in and nothing really changed. We got 12 volts at the source. We've got 12 volts at the load. But what happens if we blew a fuse? Well, if we blew a fuse, it meant there was too much current going through that circuit, too much amperage, so to speak, without any resistance. But at the same point, when I put my meter across that fuse, at that particular point, I'd measure 12 volts, even with the blown fuse. Why? Because there's a ground on one side of the fuse, there's potential voltage 12 volts on the other side of fuse, and I'm measuring potential voltage. So instead of calling it fuse voltage, let's call it what it really is. Let's call it voltage drop. And voltage drop, by definition, that's the amount of voltage that's used by a component, connector, a circuit, or a load. When we talk about voltage drop, the voltage drop really should be at the load. It should be at the component that we're powering up. But there's times because of excessive resistance and connectors, excessive resistance in wires, they're just plain corrosion. At that particular point, those components start to use voltage that was really dedicated to go out to the light or the fan or any other component. Now remember, voltage drop is the result of current flowing through a resistance. And voltage drop is the most valid test for resistance because it measures the circuit under load. So let's do this. Let's do a quick demonstration. I'm going to go through some basic voltage measurements and see what it looks like actually when we apply these principles to a circuit.